Hey everyone, welcome to today's Explainer. If you're like me, relying on AI for heavy-duty research, coding, or really any complex problem solving, you absolutely need to know about the structural shifts happening under the hood right now. We're talking about a fundamental reshaping of how AI actually works behind the scenes. Okay, let's dive into this fascinating optimization of LLM agents and unpack what we're calling the modular mind.
Think about your daily AI tools for a second. When you ask them a quick one-off question, they're brilliant, right? Like magic. But what happens when you give them a massive, long-horizon task, say deep web research across dozens of tabs or some multi-layered math problem? Usually, they stumble. Hard. They forget your initial instructions, they start running in circles, or they just completely give up. So why exactly does that happen?
Well, the core culprit here is something called long context degradation. Think of it kind of like this. An AI has a working memory, right? Just like we do. As the AI goes out and gathers search results, tries different tools, and works through intermediate steps, that memory gets completely and utterly cluttered. The really salient important evidence, it just gets buried under a mountain of irrelevant data. And when this happens, the agent literally forgets its own constraints and starts looping the same useless actions over and over again. It is a massive technical bottleneck, and it directly hits your real-world experience. To make sense of all this, here is our roadmap for the explainer. First, we'll look at the AI agent bottleneck. Then, upgrading algorithms with DPoA and GPoAB. Third, managing context with AdaCoM. Fourth, we'll explore the Fidelity-Reliability Trade-off. And finally, transferring AI management skills. All right, let's start with part one, the AI agent bottleneck. So, when an AI gets overwhelmed by contexts, it shows some very specific, very frustrating symptoms. First up is constraint forgetting. It literally just drops the specific rules you gave it. Then you've got premature abandonment, where it just throws its hands up and quits a perfectly solvable task. And third, extreme redundant exploration. Just to put this into perspective, look at this alarming stat. Without intervention, a popular agent known as Kimi will issue the exact same tool calls in 42.6% of its steps. That means nearly half the time it's just spinning its tires in the mud because it can't clearly track its own past actions. No way, right? Moving on to part two, upgrading algorithms with DAPO and GPO. Over in an open-source framework called Trinity-RFT, developers are trying to fix this by decoupling systems. Basically, they're making it so you can plug in specific reinforcement learning algorithms like modules. The two leading innovations here are DAPO and GGPO. DAPO is optimized for single-turn scenarios where you only get an outcome reward at the very end, like a long chain-of-thought math problem. GGPO, on the other hand, is built for multi-turn agents. Like when an agent is browsing the web over many steps and the rewards are super sparse. GGPO handles this by assigning credit step by step, helping the agent learn exactly which specific actions were actually useful along the way. Looking under the hood for a second, DAPO uses something called dynamic sampling. It basically drops entire groups of prompts where the AI either got them all right or all wrong, because, well, there's no learning signal there. It forces the model to focus on the tricky stuff. Meanwhile, GGPO computes advantages at both the episode level and the step level. It even uses a clever little trick called NFE_state hash to group similar environment states together. But what's absolutely crucial here is that Trinity-RFT lets developers plug these specific RL modules directly into the system. You don't have to retrain massive base models from scratch every single time. It's a real game changer. Now let's zoom out to our third section, managing context with AdaCoM. This brings us to a fascinating macro solution called AdaCoM, which stands for Adaptive Context Management. So the crucial point is this. Instead of forcing the agent to manage its own messy memory, AdaCoM brings in a second external AI to act as a manager. It's literally like having an executive assistant organizing the desk of a brilliant but easily overwhelmed worker. The main agent, the worker, stays completely frozen and unchanged, while the manager dynamically cleans up the workspace in real time. And you gotta realize, this isn't just blind summarization. The AdaCoM process is incredibly precise. First, the manager targets specific messages in the context, using their unique IDs. Second, using structured JSON, it actively modifies them. It might rewrite verbose evidence, delete stare tool results, or merge related ideas together. Only after this targeted pruning is finished does step 3 kick in. The frozen agent looks at this beautifully clean context and decides its next move. The performance gains from pairing an agent with an AdaCoM manager are, quite frankly, absolutely staggering. Just look at this table comparing the standard React baselines against the AdaCoM workflow. On complex web search tasks, the Qwen agent improves by 32%. DeepSeek jumps over 47%. But get this, look at the Kimi agent. It sees a massive 95% performance gain. It almost doubled its effectiveness simply because an external manager cleared out the redundant garbage from its working memory. That brings us to Section 4, the Fidelity-Reliability Trade-off. To understand why AdaCoM treats different models differently, let's look at this core finding directly from the research. It says, agents with higher vanilla React performance benefit from higher fidelity context preservation, whereas lower-performing agents require more aggressive compression to stay within a reliable reasoning regime. Now, what's really interesting about this slide is how it captures a fundamental limitation in AI today. Check out these context length curves. See those huge jagged spikes for the Qwen and GLM agents? That's what they call a tiered management strategy. Because those specific agents have super powerful baseline reasoning, the AdaCoM manager actually lets them see massive amounts of raw, unedited data and only steps in to compress when absolutely necessary. But then look at the lower, much tighter lines for the DeepSeek and Kimi agents. For them, the manager is using eager distillation. It's aggressively compressing the context almost every single turn because it knows those agents will get confused if their memory gets too long. It's totally adapting to the specific capability of the agent. Finally, let's move to Section 5, transferring AI management skills. Which raises a really practical question. If you train an AdaCoM manager to assist the Kimi agent, can you just use that exact same manager to help an entirely unseen agent? Well, the answer is yes, but with a catch. As you can see in this cross-agent transfer chart, and this brilliantly illustrates the point, managers transfer best between agents that have similar baseline capabilities. A manager trained to help a lower-performing agent uses that eager distillation we just talked about, which works great for other lower-performing agents. But if you pair that aggressive manager with a highly capable agent, it actually hurts performance by hiding useful raw data. You really have to match the manager's style to the agent's brain. What this all really boils down to is the immense power of decoupled AI systems. Whether we're talking about plugging in microalgorithms like DAPO and GPPO or macro managers like AdaCoM, the takeaway is clear. As users and developers, we don't always have to spend millions of dollars retraining massive frozen models to get better results. Sometimes, we literally just need to give them better managers. Let's move to and see how this builds to a final, pretty provocative thought for the day. If our working AI agent needs a smaller AI manager to keep its memory clean today, who manages the manager tomorrow? As tasks get even longer and exponentially more complex, will we eventually need a hierarchy of AI managers? Like an entire corporate structure of algorithms just to execute a single complex prompt? It's a fascinating look into the compounding future of AI architectures. Thanks so much for exploring this explainer with me today, and keep learning.